So I'm tackling this one on HackerRank called ACM ICPC team. This is an easy difficulty problem, so let's get into it. There are a number of people who will be attending the World Finals. Each of them may be well versed in a number of topics. Given a list of topics known by each attendee, presented as binary strings, determine the maximum number of topics a two-person team can know. Each subject has a column in the binary string, and 1 means that you know it, and 0 means you don't. Also determine the number of teams that know the maximum number of topics. Return an integer array with 2 elements. The first one being the maximum number of topics known. The second being the number of teams that know that number of topics. Again, these are two-person teams. Okay, so for example, if you have a list of 3 attendees with these unique sets of topics known as binary strings, this is effectively a bit set for these topics, so that's maybe some convenience that we could eke out. But yeah, so you have a bunch of these, and it looks like we're looking for what? Determine the maximum number of topics a two-person team can know. So if I put these 2 people together, they will have they have full coverage basically. So this is a total of 5, right? So these are all possible teams that can be formed, and so okay, so they're doing this thing where they're like, hey, this is a combination problem, maybe. And there's this other one, which is 1, 3. So this is like this person and this person together are missing this number 2 here. So that's what they say here. So, and then 2 and 3. So these are all the combinations of two-person teams. This could be like an n choose 2 situation. I'm wary of doing all the combinations because I'm not sure if that's completely necessary. Yeah, so in this case, the first team will know all 5 subjects. They are the only team that could be possibly created. And so you return a 5 and 1, 5 being the number of subjects known and 1 being the number of teams, which in this case is just one out of those 3. Okay, these numbers are relatively small, so I'm not worried about timing. Actually, that's interesting. I want to find the person who knows the most, or at least maybe there's more than one, right? So like in this example, that's 3 topics known, 3 topics known, 3 topics known. So each of these would be valid candidates for like the person who knows the most. And then you'd want to pair them with the next person who can fill in the gaps, basically. So this person needs 2, and this person needs this one and this one. And the person who can do that is this person here and here. So that's one team of 2 that can do 5. So 5 is definitely the answer for that. And then how many people can cover 5? Well, this person and this person actually have full coverage as well. So that's 2 teams. So that's why the answer here is 5, 2. Well, let me think about this, because I'm trying to avoid the n times m scenario. Or then maybe I shouldn't do that. Like, what's wrong with n times m, right? Like, it's fine. So what you could do, because it's a 2-person team, you can do an XOR on this and basically have like each element do XOR with every other element. And you would create or do I need XOR? I think it's not XOR, it's just OR. So you do an OR operation on each one with every other item, and then you would get your possibilities, all possibilities. You can put it into a dictionary, have a running count, and just take the highest count. I think that's like what you could do. Okay, that's an idea. Okay, so I think that's what I do. So here's my thought process here. So we have so we're doing basically big of n times n. So we're going to take each bit array, which is what I'm going to basically convert it to. Or sorry, say a bit set, I should call it. So we're going to take each bit set and use the OR operation to create combined knowledge, topic knowledge team, store in hash map or dictionary, and with running count. And then you basically just return key length of 1s and count, basically how many got counted up. I should say max key length 1s. All right, so first I need to figure out how to convert a bit string. Okay, so let's pull up a quick shell here, zoom in, go into Python land, and let's say that we take an int with 1001 whatever, and we say this is base 2. It spits out 85. So that's what I need to do. So let's keep track of things as a hash map here. Let's call these teams. as a dictionary. And then we go looping through each one for topic in topic. Wait, hold on. Topic in topic? That should be topics. It should be plural. People, come on. That's an array. It should be an array of items, plural. Okay, so I'm going to say binary string in topic, just so I can keep things as they are in the original problem. And store in hash map. Right, okay, so what I need to do here is take the binary string and to do the combinations. Let me like move this down. So I need to take a combination here. Okay, so the way the combination is going to work is you're going to look ahead, basically looking ahead. So starting from the first one, you're basically taking a combination with everything in front of it, which means that once you get to the next one, you don't need to go back one. So you can go ahead. So I'm going to do actually range here. So I'm going to say range length equals, I can't type, I swear. Range of the length of whatever we're doing, and then this is going to be I, and we're going to say for, so this is the current binary string, and that equals topic I. And what we want to do is look in front of that number all the way to the end. So I think what we're going to want to do is, well, we don't need to go to the end, right? So we can say length -1 here, because in the end, we're going to have to go through the length all the way anyway. So we're going to say for j in range, starting from I up to length, this is going to be the second team member. And this is effectively the first team member. But the second team member, we're going to loop through each one. And this will ensure that we're always like one ahead. So I actually need to make this I + 1. So you're not looking at the current one again. And so the second binary string equals topic of j. Okay, so we take the current binary string and the second team member, which is always like a person who you haven't seen yet, essentially. You don't have a combination with them. So this makes sure that the count is also correct, because you're only going to ever encounter a second teammate once. You're never going to like see them and then go back, right? You're always looking ahead, and that combination is already made. You don't need to count it twice, basically. So you can take this first binary string, and we're going to convert to int. Binary string base 2. I'm going to say or int second binary string base 2, and that will give you your combo. So the combo, this is in binary, though this is not in base 2. This is going to be in base 10. So we want to convert it back to base 2. So I need to convert it back to base 2. How do you do that? I think you can do a formatting thing. So this is what I've seen, actually someone recently, that you can take the, I think like that. Is that correct? Format 23? Is that a thing? Yeah, there you go. Okay, so that is what I'm going to use. I'm going to use this formatting to convert it back into a way that we can work with. That is also unique. So we're going to format on the combo. So this is the team, I guess, combo binary string, because that's what it is. So this is going to be the binary string of that, and then we can store that in a hash map. Let me move this over. It's fine. And take a running count. Okay, cool. So that means, so now we just do our normal thing of like, okay, if this combo string not in our teams dictionary will start with 0. Otherwise, we take that and we just add 1 to it. And so we're just going to keep running some of the total teams that have that particular combo. Okay, so I just want to return this right now, see what this looks like. Return teams. So just return teams. Let's see. Let's run some code, see what that looks like. Okay, so my output is this. It expected this. Okay, fair enough. So what we're looking at here is interesting. So I think, so the output doesn't look like a dictionary, but I think that's because of the code that's in place to get the output to be formatted like this. I think it's formatting it in a way that it's like looking at the values. So what we see for this first one is the combination of this and this put together, what the first team of 2 looks like. And that looks correct because all the ones are kind of in the right place. And then you go from here to this one and this one. These two together will make a full one of ones, and then all the combinations after that, basically. So this is looking proper. So now what I have to do is now the kind of somewhat messy part, which is to look at all the keys and get the one with the largest number of ones. So that, I think, is a different issue. So max length equals none, 0 for now. For a key in teams.keys, so we're going to take the count of each key. So these are going to be strings. So we're going to say for that we want to get the key.count1. That's going to be our count. And we just simply take the max length as the max between the current max length, and the current count. Count of ones. Count of ones. Okay. So you get the max count of ones, and then you can return the sum of the max length of ones, right? Okay. So I'm going to be a little cool about this. I'm going to just do my return here. I'm going to do a little list comprehension. I'm going to go for key count in teams.items, and I only want the items with the max length. So if key.count of 1 equals the max length that we found out in the last one, and then the thing we care about are the counts. So count, and then in the end we want to sum all of that. So there's one very long list comprehension, but that's basically what we're doing. We're looping through all the keys and values in the teams dictionary. We are filtering only ones that have the max length that we are looking for, and then we're going to sum all the counts up, and that's all that's happening there. So let's run some code, see what happens. I got an error. Int object is not iterable because of mapping. Okay, line 59 it says. Oh, right. Okay. Right. So I'm not supposed to return just a sum. I'm supposed to return two things. So let's not do that. Okay, so I need to return the max length and that as like a dictionary here. So this is the team sums, that, and I'm supposed to return two things: the max length and the team's sums, I guess. All right, so return some code. It's supposed to be a length of 2. It's supposed to be like 5 and 2. So we ran some code. It looks like it works out. Let's submit some code. Okay, not too bad. That was not that. I mean, I would say that was not the easiest one. All right, I wanted to go over the time complexity for this one, and it looks more complicated than I originally gave it credit for. So going through the first list, going from the initial range, that's definitely big O of N for that. As we get down to the second team member, we're basically kind of looping through N members again. It does reduce over time though. So like the first time you go through it, it's like basically the full N, but as you get closer to the end, it's less of that. But in the end, it's still all depending on the size of N in the first place. So I'm going to put that as big O of N for now, because I think the total is like N divided by 2, or like 2N or something. I think it's like 2N, and so it's a constant that you could just drop basically. What's interesting is this part here. So this conversion of a string, the conversion of that binary string to an integer, I believe requires going through the entire string, the length of the string. And that I think is the same. And actually, if you look up top, they tell you that M is actually the binary string length. So M is the variable I'm going to use for this. And it's going to be big O of M for that. It's going to be 2M for this operation, but 2M gets reduced. Again, you drop constants. So that is good. I'm not quite sure about the formatting. I'm going to kind of discount it as either being negligible or at most big O of M anyway. So it's going to reduce to M anyway. So this whole thing is kind of like its own beast. So I'm going to add that to my total time complexity at the bottom as big O of n times m. That first part. Second part here is this loop. This one is going through all the keys, and if you assume the worst case scenario, all the keys will be basically effectively like a unique combination of teams, but that is essentially all the teams that were made up here, and all the teams that were made up here is big O of n times big O of n. So this is going to be n squared, just out the gate, because that's the number of keys. You don't factor in this part because that's just part of the time complexity of like getting the calculation done. But once it's done, it's stored as just a number of keys, and that's big O of n squared. This counting is actually subtly doing some iteration under the hood, and it's basically looking through each character in the string, and so this counting is actually big O of m as well. And you know, max length, all that stuff is constant, so this stuff is negligible. So this step here can be calculated as big O of n times m. You know, starting to see a recurring count there. This part here, even though I made it into list comprehension, there's still iteration, of course, going on. This for loop is going through each item. That's the same thing as what we saw up here. So this is still, you know, big O of n times n. And then you're looking for each key you're checking you're using this dot count method again, which is still doing big O of m. So that is what's happening there. And that is everything there. The summation is actually going through this entire thing. So that step is technically going, it's like a second loop that's just going through all the elements. So that you can consider that to be just big O of n squared again, n times n. So this looks like a very big nested, this looks like a very big complex problem, but let's think about like how this thing gets reduced, and eventually this becomes just the most significant component. So effectively you have 3 of these. You can even see the highlighting. So it's 3 times that, or I could say 3 n squared times n, 3n squared times m, plus big O of n squared. And if you think about the factors, the thing that is most significant, it's definitely this step here. And then that becomes the most significant component. So we basically drop this one because it's not as significant, because you're multiplying by m. Oops. Because you're multiplying by m on this side. So that's why this one gets dropped out. It just gets ignored. You have to assume that these numbers are very, very large, even though I know that's not exactly the case for our specific situation. We can assume that for time complexity, and then we basically just drop the constants after that. So this becomes big O of n squared times m. I believe that's what it comes down to. There's definitely a lot going on here, so you know, feel free to correct me on this if I'm wrong, because I'm not perfect either. So let me know in the comments for sure. All right, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time.